Welcome, everyone. Today, I'm excited to introduce our groundbreaking N-dimensional data compression technology, or NDDC. This quantum-enhanced fractal compression method represents a paradigm shift in data storage and transmission capabilities, with applications spanning nearly every data-intensive industry. Let's start with an overview of what makes NDDC special. As you NDDC works by projecting data into higher dimensions between dimension 3.5 and dimension 7 and higher. What's revolutionary is how compression scales exponentially with dimension, following the formula 2 to the power of dimension 3. Looking at our comparison chart, traditional compression methods like ZIP achieve around a 3 to 1 ratio, while standard fractal compression reaches about 100 to 1. But NDDC at dimension 6.6 achieves an astonishing 10,000 to 1 compression ratio while maintaining lossless reconstruction with error rates below 10 to the power of negative 15. So how it works. I can show you the mathematical foundation behind NDDC. The core projection function you see here maps into higher dimensional spaces using quantum principles and fractal mathematics. This interactive slider demonstrates the exponential relationship between the dimensions and the compression ratio. At D3, we get no compression benefit. At D4, we achieve 2.1 compression. By D5, it's 4.1. But watch what happens as I increase the dimension further. At D6, we reach 8.1. And by the time we hit D6.6, we're all the way up at 10,000 by 1. This isn't theoretical. Our early implementations have already demonstrated 4 to 1 ratios on quantum simulators, with much higher ratios expected as quantum hardware matures. So what? So what can we do with this? In media streaming, we could take Netflix's entire 3.5 petabyte library. It could be compressed to just 350 terabytes, enabling entire catalogs to be cached locally with minimal bandwidth. For healthcare, which we particularly focused on, look at this chart showing genomic data compression. A 200 gigabyte human genome sequence compresses to just 20 megabytes. Similarly, 4D medical imaging that once required terabytes can be reduced to gigabytes or less, revolutionizing telemedicine and patient data portability. Climate scientists can work with complete high-resolution data sets rather than downsampled versions. AI models can be compressed to run on edge devices, and scientific institutions like CERN can make their vast data archives more accessible to researchers worldwide. Each card highlights specific benefits for those sectors, from cost savings to performance improvements. Let's examine our Netflix case study in a little bit more detail. Using NDDC at dimension 6.6, the impact on streaming infrastructure is profound. As the chart illustrates, storage requirements drop to just 0.01% of current needs. Imagine storing 10,000 movies in the space currently needed for just one. Bandwidth consumption falls to 0.1%, enabling 4K streaming even on limited connections. Energy usage decreases to just 5% of current levels, with corresponding cost reductions to 3%. These metrics fundamentally change the economics and accessibility of high-quality streaming services, potentially bringing them to regions with limited connectivity infrastructure. Finally, our Future tab outlines the development roadmap and broader impacts. We're projecting a phased rollout, dimension 4 compression for archival starting in, say, 2025 through 2027. Dimension 6 for streaming by 2028 through 2030, and mainstream adoption of dimensions 7 and higher by the 2030s. impact spans three dimensions: environmental benefits with 90% energy reduction, global access, bridging the digital divide, and enabling entirely new data paradigms that were previously impossible due to storage constraints. So thank you for your attention to this demonstration of McGinty AI's NDDC technology. This quantum fractal approach to data compression represents one of our most significant advances in information technology of the decade, with the potential to reshape our digital infrastructure fundamentally. I'd be happy to answer any questions about potential applications, our technical approach, or our implementation timelines. NDDC is currently data agnostic, but it particularly excels with high dimensional data like video, genomics, and scientific data sets, which contain intrinsic fractal patterns. The current implementation requires 50 to 100 qubits for dimensions 4 to 5 with coherence times above 100 nanoseconds. For dimension 6.6 and beyond, we're targeting 1,000 qubit systems with the MEQ integration for stability. It is truly lossless. So unlike traditional lossy compression, NDDC maintains reconstruction error below 10 to the power of -15 through quantum superposition. That preserves information within the higher dimensional projections. And really, the main competitive advantage of this over all traditional methods is the exponential scaling with dimension. That's the key differentiator. Traditional methods hit asymptomatic symptoms around 100 to 1, while NDDC can theoretically achieve millions to 1 compression at higher D values. Thanks for your time.